we talked about convolutions and convolution CNN structures, and before that, so we have to know what convolution operation means, and because in the convolution operations in one-dimensional space, and here is some of the examples of convolutions. We can make the corrected signal smooth, or you can detect the sharp changes by having proper the corner design, and images generated in two-dimensional space and colored, and gray is the same as the matrix. And so for 2D convolutions, this is actually, you have to remember, we do element-wise multiplications. After that, we do summations to get single point. And the mask or corners or filters going to shift it like that. So that's and the idea of that is for artificial neural net, for ANN, is that something that I don't like it is at the end, you have to, or for the input image, we have to flatten it out. So that's kind of something I don't like it. The reason is that it does not make use of the spatial structures, right? So that's why we do convolutions and the image and things that you have. It's this image is I want you to so I mean, this is related to ANN, and this is CNN structures, and the shift we shifted the mask. That's kind of representative animations that you're supposed to remember. And the key contribution for CNN structure is weight sharings and local connectivities, and typically or generally have sparse interactions. That means you're gonna have a few number of parameters that we need to estimate, that we need to predict or learn from the data set. So that's one of the big advantages of CNN structures, especially when you have input as image. And here, what do you mean by multiple corners and things like that? And what's the definition of channels? And here, let me show you the animation again. So this is when you have 3 channels, and this will be the corners. We do like that. So by having that, we're gonna have single value, and we shifted it to get. And for multi corners, and then this one, since we have 2 corners, we have 2 layers in the output side, and that's the paddings as right. And here is the stride. You can easily understand from this animation. And the padding is sometimes we want to keep the same dimensions for the input and output. So we add zeros at the end. We call it zero paddings. That's how we do. And that's the animations that to explain it. Explain for paddings and stride. And also, the CNN structure have nonlinear activation functions as well. So that's what we covered last time. And here, let me continue on the poolings. And pooling is, I mean, there are a lot of sense, but don't worry about it. And so this is the input, and we do poolings, and it's going to be outputs. The idea is that if have, let me see, if we have 2 by 2 pooling size, that means we do like that, and we take the maximum values, so we call it max poolings. For the max poolings, we pick the maximum values, let's see, and we don't overlap, and we shift the windows and pick the maximum values over here, like that. So that's what max pooling does. I mean, it's extremely, it's not complicated, and just, I don't think there's no difficulties to understand this. And one of the benefit is that here we first in input side, in input side, the size is a 4x4, but by having 2x2 filters for the max poolings, the output size is 2x2. So we gonna reduce the the the, the spatial resolutions or the size for the faster computations. You can think of as here is a, it's an information compression, right? And let's see, another one is that something you want to remember is from here you can compute it, but in the opposite side that you cannot. Having this, sorry about that. This is not a reverse is not a reverse process. What if this in the having this, we are not able to reconstruct the inputs. So that's the, so it's not linear process, it's a nonlinear process. And let me show you the poolings in one-dimensional space just for the demonstrations or illustrations. Suppose we have that kind of inputs and say that what's the size of 2, and we can pick right over here and pick over here, this one and this one and that one. That's max pooling, no difficulties. Right? Or we have average poolings. If we compute the average values per block instead of max values, it's really up to you guys. Sometimes probably having the average pooling instead of the max pooling is more reasonable, or something that you have to decide. But this one, max pooling is more typical way that I embedded or implemented in the general CNN structure. And this one is something that I like it. So let me show you. So that's one of the advantage, was one of the reason or the advantage of having pooling process operations in the middle is that it's invariance. What do you mean by invariance? So suppose this is the input, and this will be the output of max pooling, right? So pick the maximum one, pick the maximum one. But what if we have the somehow the input, suppose that input is shifted like that somehow, but as you can see, having the max pooling process, the output does not change, right? So say in the inputs we have a lot of variance and noise and uncertainties, but by having the max pooling process or operations in the middle, the downstream side of the neural net, we have invariance properties. And that's the, so say, suppose we have small perturbations or deformations in the input or upstream side. I will say here is upstream, here is downstream. Say deformations or noise or variations or uncertainties. But after here is here is more like invariance. That's big advantage of having the max pooling or pooling operations in the middle layers. So let's think about the case that we have. What if we have multi-channels? The pooling is like that. So over here, we pick the max, suppose that max pullings, so pick the maximum values. The shape is different from the convolutions. And one thing they should notice is there's no, the parameter is related. So let me see. So pick the maximum one, like that. Okay, that's we are doing max pulling process. So that's I have multi-channel, we're supposed to have the same number of channels. C and C should be the equal. I mean, I'm repeating the shape or structures because it's so important when you implement it. So I want you to make sure that you understand the shapes and related to like convolutional operations and the max pullings and things like that. So that's we did that. So for convolution layer block, that is gonna be the basic unit. What do you mean by, say, have inputs and we do the convolutions and nonlinear activation functions, and then we do followed by pullings. So we can say max. So there will be the convolution layer block. So in each block, we do convolutions and nonlinear activation functions and max pullings in each block. And in CNS structures, we repeat that. Let me see. Oh, here is in the convolution layers, we have convolution states and nonlinearities. We add that, and pulling process. It will be the convolution conv layer, one conv layers. And in classic structures and convolution neural net is we have input and outputs, and we have many conv blocks. So we'll do convolutions and the convolutions and or say inputs and conv block. We probably have another blocks. I don't know, it's like many times. Then at the end, we say at the end we will do fully connected layers, which means is we gonna flatten. We're gonna do flattening to say if that's classification problems, we do softmax for the multi-class classifications. So by having this kind of structures, we're gonna believe that, say, in CNS structures, if that's we do throughout this process up to here, it's a kind of the feature learning process based on the image. That's the kind of the general structure of classical CNN structure. So we can use CNN sorts of classification problems, and it's going to learn the features in input image through the convolutions. That's what, so this one is what I mentioned here up to this point. And of course, it's gonna introduce the nonlinearities using the activation nonlinear activation functions. And for the pullings, we're gonna reduce the dimensions because we're going to reduce the size of the matrix and preserve the invariance, spatial invariance that I explained. So in general, we have from here input, and we do at the end we do classifications, but in the middle these combo layers for is gonna acting like it's gonna act like feature learning process. And at the end, we do flattening, do fully connected layers for multi-class classifications. In typical ways, we're gonna use the softmax, like what I explained for the binary classifications, in logistic regressions. For the multi-class classifications, it's gonna be the softmax. Right? In general, in output, we're gonna do one-hot encodings. So each neurons is gonna tell us that the probability of that image is belongs to the particular class as a one-hot encoding type or style. How do you train? Again, for CNS structures, we're gonna do the backpropagations, and you're gonna run the weights of convolution mask or corners or filters and fully connected layers. So it is the weight and bias as well. And for using the backpropagations, and the loss function is for classification problems. Again, it's gonna be the cross entropy loss. Pretty much the same. Here in the CNS structures, the only difference is the type of inputs. Now input is probably image or multi-channel image or like two-dimensional space. So for specialized data structures, instead of we're gonna implement the convolutions, and at the end we have linear classifiers. That's let me so let's do. So for what I want to do, again, like I said, so I think one of the easiest, one famous the example is using the MNIST data set. So here is the MNIST data set, and like I mentioned, for MNIST data set, it's a flattened out. So actually, the input size is like 28. What's the size? 7. So that's the size of MNIST data set. So now, as you can see, for CNN structures, we have the input should be the matrix. So I'm gonna, before that, I'm gonna reshape. So we need to reshape it. The inputs to like that. And using that input as an image, we're gonna do, let me see here. So this is the exact structures that I want to implement it. And let me ask, how many classic convolution blocks or layers in this figure? How many convolutions? How many convolution blocks? One or two or three or four? So I'm gonna do 2 conv blocks. I mean, there's no reason. I mean, just I just tried it and it works okay, and the classification accuracies I think is a reasonable set, but this one is not a like optimized structures. Okay, but it's I think it's okay, or it's good enough to demonstrate. Let me show you. Here, what I'm gonna do, the input is 28 by 28. The corners, the first is gonna be the 3 by 3, and the number of channels it's like 32, and we're gonna do max pullings by 2 by 2 window size, and keep the same number of channels. Now then, we're gonna do another convolutions, and with this number of channels and things like that. And let me ask, and over here, how many corners we need, or are they? Over here, how many corners?
3? No.
So corner size is 3 by 3.
Yeah.
How many corners?
9.
No.
No.
Corner is like, this is the corners, right? The related weights are 9, but I'm asking how many like mask or corners or filters
Okay.
over here. So in order to answer that questions, let me go back to this one. So you can think of as this one is 28 by 28 MNIST image, and in output is here 2 channels, and we need 2 corners. But in that example, it was, I think it's 32 channels. Then how many corners do we need?
32.
32, right? So in the single image, if you have corners like that, we will do, and I'm gonna make it image, right? And do another corners, we wanna repeat it. I'm gonna make another image like that. So here, the number of corners are same as number of channels, right? And let's go back to how many. Here we have 32 channels. That means in TensorFlow, there's having 32 corners. This is something that I need to decide, I need to determine. And from here, I'm gonna do, so and then over here, what's the size? What's the size? Okay, that, this. We do convolution.
3 by 3. Yeah, 9.
Yeah? Say that again.
9?
9?
It's 3. Yeah.
So in the input image is 28 by 28. We do 3 by 3 corners. We're gonna do like that. And what's the size of the output?
Okay. 28 divided by 3.
But we're gonna do paddings as well. 0 paddings. to keep the same size. So in here, we have 32 and the same size, and followed by max poolings with 2x2 window size, and does not change number of channels. It's gonna be the same. But what about the size of this guy? This one is 28 by 28. For that one, let me go back to answer that question. Just think about this. So it was 4x4. We do 2x2 max poolings. It's 2x2. So it's like, so if this is 28, 28, 2x2 poolings, what will be gonna be the size? What do you think? It's gonna be 14 by 14, right? Yeah. So that's so now here it's a 14 by 14. Okay. Now having 64 channels, and this is tough questions. Probably that's the question that we're gonna be the final exam. How many kernels here? How many kernels?
64.
64, yes. Okay. What's the kernel size? I mean, number of kernels, I think 64. What's the kernel size? Here, 3 by 3. And what's the number of channels?
65. 64, sorry.
No.
No?
Because the input.
Because of the pooling.
Yeah.
Okay.
And for that one, let me go back to just think. I think about this. Think about this. Probably this one. Okay, that's the kernel size. It was in the previous was 32 channels. That's why 32, and we have 3 by 3 the height and width. And over here it was a 64. That's why we have 64 kernels. Everybody is happy about this? Okay, so we go back to where we were. And then at the end, so here, what's the size?
14. Oh no, 14.
Yeah, that's
14.
Then we do another max poolings by 2 by 2. Then what's the size?
7, 7.
7, 7, right?
Mm-hmm.
Now we have 7 by 7 and 64 channels. Then we're going to flatten. Then how many neurons?
64. Passionate. No.
Here in here, how many pixels do we have?
Oh no, yeah.
Here we have 7 by 7. We have 64, right? That will be, so we're gonna flatten out, so it will be number of neurons. then at the end probably is MNIST data set is for 100 encodings. We're gonna have 10 outputs, and this is hidden layers. I don't know. I'm just gonna have 100 or 200, whatever that I want. So that's the entire CNN structures that I'm going to build. That's something that I designed. Again, it's not optimized, but the only purpose that I want you guys to think for each step, what's the size or number of how many channels and the corners and things like that. I want you to you understand 100%. So let me see. So input height h is 28, width is 28, and input channel is 1 because we gonna deal with grayscale, right? And that's the shape of input layers. The reason that I have none here is going to, because again, remember, if you remember, is this we're gonna use a backpropagation, which is a gradient descent, and I'm gonna use mini batch gradient descent. So it will be number of batches. It's a batch size, but it's not, haven't decided yet, so I put it none. For first convolutions and the second convolutions, and at the end we're gonna do fully connected. So that's the corner size and h and height and width. And let me see that one for the output channels and 32. And the pooling size is 2 by 2, and at the end over here it will be the size is 14 by 14 and 32 channels, and again it's a batch size. So we are here at this moment, and followed by second convolution layer, and again it's corner size and output channels 64 and the poolings and 2 by 2. So up to this point it's 7 by 7 with 64. That's the, and I'm going to flatten the features. That means this one is, just same as here. It's a 7 and 7 and 64. So that's the convolution result side, and I'm gonna have hidden over here. This over here is 7 by 7, 64, and over here 100 will be 10. That's the CNN structures that I want to implement, or for that's the structure that I designed. And over here we have the TF dot variables, which is all the weights and bias that we need to learn from the data set. And for convolutions, for the weights, we have conv1 and conv2 layers and hidden layers and output layers, and we repeated that in the same name with the weights and bias. And for this is gonna be the TF dot variables. We have the corner size and the input channels and the output channels. And for the second layers, it will be the corner size for the second conv layers, and this will be the input and the output channels for the conv2 layer. And hidden layers is same as the fully connected, so it will be, again, it's flattened. So conv reserve side over here is that I'm going to use that. I'm right here with number of hidden and the hidden layers and the number of outputs. For the bias, just keep the rock. So that's the tip that And for this is going to be the supervised classification problem. That's why we need input and output. So I'm going to put it in this as a placeholders. And so here is 28 and 28, and we have a single channel for the grayscales. The output is going to be the 10 digits. So it will be 100 encoding. So it's going to be 10. That's for the placeholder. So I'm going to build the models. So input and weights and bias, and we have tf dot nn dot conv 2D because we're gonna do convolutions in 2D. So you have x, and these are the weights and stride. So you guys remember stride, right? So we do these two. So remember in here is in the batch, and let me go back to H and W. Oh, over here, that will be the, so it's number batch side and height and width and channels. That means I'm gonna do stride for batch. I'm going to one bit. So that means I'm going to cover all the batches, and the height for the stride for the height is 1. For stride for the width is 1. Stride for the channels is 1. So I'm going to cover entire. And the paddings here, we have, for the paddings, here is the filter size is, it's 3 by 3. And for stride, it's the stride of sliding windows for each dimension of the inputs that I explained it already. And for the paddings, and let me see, and there's only 2 options. If we put the same, that means we're gonna do 0 padding. So we're gonna keep the same size for input and outputs. For valid, there's no padding. So in general, it's going to have a smaller dimensions in the output side or in the downstream. So here we same means we do 0 paddings. Any questions?
No.
And then after that, we do nonlinear activation functions, and you can use sigmoid or tangent, hyperbolic, whatever. And here we do values. So there will be the inputs and the outputs, and followed by the max pooling. The max pooling will be the, and here it's a kernel size is 2 by 2. And if you remember poolings, there's no overlap. So the stride should be the same as the window size. So here again, it's 2 by 2. And for the paddings, if you go back, we don't want to keep the same size, because after the paddings, it should be this smaller, right? So in that case, there's no padding. So I'm going to use a valid. That's for first convolution layers. I'm gonna repeat it in the second convolution layers of the point here. The only difference is that it should be the same, but here inputs and the input for the second layers should be the output of the first layer. And then over here is max pooling 2 is with the output of the second convolution layers, and I'm going to reshape it to flatten. Then over here, just fully connected using that ones to add hidden layers, and we do nonlinear activation functions, and the output layers, the output going to be the output of this neural net, like that. So let me repeat it. You have max poolings, and for the second convolution layers, and followed by fully convolution layers. So it's the form of flexing the features, then apply the softmax for to multi-class classification problems. So that's the, I mean, what I'm saying is that this one is the same as these structures. I mean, this one is, the structure is visualized, but in order to the TensorFlow to understand these structures, you have to write it this way so that the computer can understand or recognize it. And for loss and optimizations problems, again, it's a multi-class classification. I mean, I think it's now at this moment everyone knows that it's cross entropy. You're going to use that, so there will be, and for same as softmax. And optimizers, you can use whatever optimizer that you want, or the TensorFlow can provide us. So the inputs and weights and bias, there will be the predict values. And what I want to do to loss is I can use softmax cross entropy with the logits. And this will be the true labels. And this one is the lots going to be the output of the neural net. And I want to make sure these two are pretty much the same. That means I have to minimize that. And since they have a mini batch processor, we need to reduce means to get single scalar values and use that loss to minimize it using this kind of running rate using adder optimizer in this case. And in order to optimize, we have here, I use 50 as a batch size. So each iterations, I'm gonna randomly select 50 among the training data set. Right? There will be the maximum number of iterations. And again, I need to open the sessions and initialize it and things like that. And here in MNIST and training, in the next batch method, here is 50. I'm gonna randomly select 50 of them and put it in the train X and train Y. But here is, this one is 784. So I need to reshape it to 2 by, this one is 28 and 28 is 1. And this one is, it's a batch size. Then there will be the train, and in order to optimize, we use feed dict in placeholders X and placeholder Y. I'm going to put it in train X and train Y to run it. Then once we're done, say I randomly select 100 in the testing data set, not the training data set. So to evaluate it, to see whether these true labels and might predict whether it's, I counted number of these values are identical, and say it's only 3 of them are mislabeled. So that will be approximated, the accuracy is like 97. Or to get 1, let me see if this is the input, and the predict values, this is like the output of neural net. So this is 100 encoding, so I know that this is 1, 2. So that's the right predicted values. And I think I showed you before. I implement the CNN structures over here, and in the real time, it's evaluating. Whenever I press the buttons and take a pictures, and over here take a pictures and make it in 28 by 28 grayscale and put it in CNN structures, and at the end we have the 100 encodings and take the maximum values and display it. That's how I implement.